Howdy future geographers, welcome back to Geography 110. Today we're going to be talking about some really cool topics and I think you're going to enjoy today's class. Specifically, we're going to be looking at the exciting world of landslides and what your book refers to as mass wasting. Then about halfway through class, we're going to completely change gears and examine something that the book really doesn't do a good job explaining, and that's going to be both groundwater and surface water. But today's class, today and well, probably a little bit on Friday too, we're going to be focusing on groundwater. And then we'll move a little bit more into surface water in Friday's class. So with that, let's go ahead and get started. Before we get going on today's class, I'd like to spend a few minutes talking about Sakai. First of all, I really want to apologize about the quiz that occurred last weekend and some of the confusion associated with the feedback system. Hopefully, I have been able to isolate the problem and we won't have that issue in the future, but if there's ever a question, just feel free to email me and I'll try to do my best to figure out what the problem is. And even when I can't figure out what the problem is, I can always just add more, give more opportunities for students to provide responses to the quiz, such as what I did this past weekend, opening it up. I believe I actually ended up giving 4 chances to retake the quiz in total. Anyway, so with that said, always feel free to email me if you have questions about that. The second thing I wanted to talk about was the weekly recaps. I realized just this past week that whenever I post a response, sometimes y'all aren't able to review my in-forum responses to your questions. And so what I've gone ahead is I've turned all of the weekly recap forums back on, but I've locked them so that they can't be changed. And then that way you can see that if you asked a question, odds are I may have responded to it, especially in the last 2 or 3 weeks. And of course, if you have any other questions, feel free to either email me directly or take a look in the forum and see what's going on there. So what did we learn last class? Well, basically we were talking about weathering. We were talking about the differences between chemical and physical weathering. We talked about the various sorts of elements that impact weathering. We discussed bedrock and how bedrock can begin to be weathered away. And then we took a look at some really cool landscapes associated with karst landscapes. So thinking about caves as well as towers and cockpits, and even took a quick look at the video, The Man with the Golden Gun, as James Bond flies through Thailand and sees those amazing towers that are visible from the air. We're going to be continuing with that same theme. Not necessarily the caves and the karst landscapes, but a little bit more with the weathering. And really what happens whenever you have an event where weathering occurs perhaps all at once as opposed to over a long period of time. So what do I mean by weathering all at once? Well, what I'm referring to is mass movement. And basically that is just how soil, sediment, sand, and rock moves down slope as a mass, largely under the control of gravity. Now, mass movements can be either slow or fast, and they can have a really major impact on humans, as we're going to be talking about associated with your assignment 3. They can occur even in the ocean, where sometimes there are really big avalanches, and those avalanches or ocean landslides, as I believe they're actually referred to, can cause things such as tsunamis. And in fact, one of the greater threats to the North Carolina Outer Banks is the fact that an ocean landslide could occur not too far from the Outer Banks, therefore creating a tsunami. We also see mass movement on other planets and places where there's some dirt and some wind. You know, there's been a lot of discussion about landslides on Mars, for example, or on some of the planets surrounding Jupiter. Not planets, excuse me, moons. There are lots and lots of different types of mass movements, but I think it's pretty easy to go ahead and just like combine all of them into three main categories. And we can think of those categories as falls, slides, and flows. And those falls, slides, and flows correspond directly with the characteristics associated with that particular type of mass movement. So let's focus on the first main category, and that's going to be flows. And a flow is like whenever the land moves as a spatially continuous movement. Basically, the land acts like a body and travels like a liquid, like a river almost. And we're going to be taking a look at three different fast flows and two different slow flows. So the three fast flows that I want you to be aware of are rock avalanches, debris flows, and mud flows. And frankly, they all sort of act similarly. They all act like a river of sediment moving downhill. The rock avalanche its consistency is going to be mostly composed of very large rocks or even boulders that have broken away from the bedrock. Rock avalanches move very fast, but they move sort of in a continuous fashion. Debris flows, on the other hand, is very similar to a rock avalanche, except it's going to be composed of a mixture of rocks and soil. And it's going to be moving at a medium to quick speed. And I have a video here that a hiker took while they were walking around Aconcagua, which is a large mountain near the Argentine-Chilean border. Here, let's take a look at this debris flow. I don't know about you, but I think that is super cool. And to think that that debris flow had very, very little water in it. In fact, that was mostly just soil and rocks, just flowing like a river down through that small canyon. Mud flows are very similar to debris flows, except they're going to have almost no rocks. And it's going to be composed a little bit, have a little bit more moisture associated with it. Heck, a lot more moisture associated with it. And so you can think of sometimes whenever you, maybe if you go on YouTube and you type in a mud flow, you might see some large kind of like water soil mixtures traveling downhill at high speeds. That's going to be a mud flow. So those are the three fast flows. There are two slow flows too, one of which is going to be soil creep. And soil creep is a very slow and very dry mass movement that's associated with associated with both temperature and gravity. Temperature and gravity, two key components of soil creep. So what does this act and sort of look like? Well, what happens is that you have soil, it's sitting on the ground, right? And as that soil warms up during the day, it's going to expand, 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 and then which sort of elevates it, lifts it up a little bit from the ground. But then at night, it cools down, right? So that soil begins to contract down a little bit. And as it contracts, it falls down. Well, if that soil is on a slope, every time it rises up, it sort of elevates itself a little bit. It's sort of positioning itself to fall down the mountain just a little bit that night. And so this is caused by shear stress, and shear stress is merely the slippage of a geologic object past another. So you can think of this as the soil just sort of rising up a little bit And then as it falls back down, it exerts a little bit of shear stress and sort of moves with gravity downhill slightly. Like I said, the cause of creep is mostly due to temperature, sometimes due to a little bit of the moisture in the soil too, but predominantly it's going to be temperature. And so you can see, for example, in this photo that I took on the side of a mountain in southern Argentina, this particular tree, right, is bending slightly, and that's because the soil is creeping. It's creeping downhill, but the tree is trying to stay in the vertical position. And so instead of the tree tilting to the side, it's going to continue to try and stay at a 90, or try to stay vertical. You can see an even better example here from the University Space Research Association, where the roots are trying to kind of go downhill, and in any other circumstance, this tree would be pointed at an angle off to the side, but the tree instead is trying to point straight up into the sky. This is a tall tale sign of creep occurring whenever you see these bends in trees like this, especially when you have a whole bunch of them bending. I have a little bit of soil creep going on at my ranch here just outside of Fort Worth, and we can see it here on this fence, which was installed probably 25, 30 years ago. And so you can see how this fence has started to, the base has started to kind of warp out a little bit. And so that is due to soil creep, that sort of tilting action. You can see here my neighbor's fence doing almost the same thing right in here. You can tell that this base is starting to move downhill, and as a result, it's kind of tilting a little bit. You can see it most significantly right here at the joint between the fence and the gate, and how far the fence has tilted relative to the gate, which is hinged on one side over here. So the second main type of slow flow that I want you to take a look at is solifluction. Solifluction is due to the freeze-thaw cycle associated with soil. And so what happens is that as the soil expands, when it has a little bit of water in it, it expands when it freezes. And when that expansion occurs, again, it just sort of like the creep, it rises up a little bit. But then when it thaws, the soil thaws, it falls downhill as it begins as the soil particles begin to contract a little bit. So freeze, you have expansion, rise up, and then with the thaw, it contracts down and falls downhill. This occurs very, very, very slowly. But all right, so how do you recognize this on the landscape? Well, it's almost always going to occur either at high altitudes or in high latitude environments. And you will see it frequently as sheets or lobes. So you can see here on this landscape, you can see it's sort of like this slow creep that's going to be going down the side of the hill. Not creep, excuse me, solifluction going down the hill. And it looks like, you know, in this particular instance here, it kind of looks like a lobe, whereas back over here, it kind of looks like sheets just moving down the side of the hill. So this typically occurs on slopes that are between 5 and 30 degrees, but can sometimes occur sort of outside that spectrum. And as I said earlier, solifluction lobes may only move a few centimeters per year, so it's going to be very, very minimal movement. All right, that takes a look at flows. What about falls? Falls occur, and I just want to make a quick note. This slide has changed rather significantly from when we posted it on Sakai. So just be aware that the slide has changed. So falls are generally dry and they're fast. And it's when fragments of rock or soil detach and slide down a cliff or a mountain. And as opposed to a flow, which sort of looks a little bit more like a stream or a river, a fall is probably something that you see when you've been driving around and you see like giant rocks that are piled at the base of a cliff. So whenever you have a fall, it creates what's called a talus slope. An a talus slope is just going to be the broken bits of rock that form at the base of a mountain. You can see a talus slope here in this example from a photo that I took when I was traveling through Alaska. Obviously, there was some sort of fall that took place here, and then as that fell down, it collected at the base of the mountain and created this talus slope. Now, there are three primary types of falls. You have rock falls, which is of course going to be really big rocks. You're going to have debris falls, which is going to be some rocks mixed in with a little bit of soil. And then you're going to have earth falls, and that's just going to be all soil and fine sediment. You might see some of this. I've noticed whenever I've traveled to California and walked around where you have big cliffs kind of right up against the ocean. Sometimes the cliffs are made of fine sediment, and so when that happens and there's a fall, you're going to have a bit of an earth fall because it's going to be almost entirely soil and fine sediment. In this particular situation, this sort of looks a little bit more like a debris fall to me. You can definitely see some large rocks mixed in with the soil. The third main category that I want you to take a look at is going to be slides. And these are a little bit trickier to kind of wrap your head around. But a slide occurs whenever you have a mass movement, but the mass movement generally doesn't move too far away from the site where it occurred. It's sort of similar to the falls that we were taking a look at earlier, except whenever you have a slide, there's usually a little bit more moisture involved. And like I said, they don't move quite as far away from the side of the hill. So with the slide, the land moves as a single mass, and it has intermediate speed and water content. So you can see here, this is from the trip up the side of the volcano in Nicaragua. And you can see here that this land has broken away from the side of the mountain, but it really hasn't traveled that far. You can tell also that it's sort of moved as one giant mass. That's what I'm referring to as a slide. And slides are sometimes also referred to as slumps, just be aware of that. So there are two primary types of slides. You have the translational slide, which is when you have a 20 to 45 degree slope, and the contents just translate down the hill with very little rotation. Rotational slides or rotational slumps move along a surface that is concave or curved. And again, it's going to be sort of similar in terms of the angle of the slope. And the contents break away and give the appearance of a bit of a bowl shape. So what does this look like? Well, here we have an example of a translational slide in a figure that I stole from the USGS. You can see here, right? The land has detached and moved away from where it was previously, but it hasn't moved too far. You can see that here in this particular photograph too, where the land, this is either a translational, it sort of looks a little bit more like a rotational slump. Sort of has characteristics of both translational and rotational. But you can see this particular slide has moved away, but it hasn't, necessarily kind of fallen all the way off the side of the hill. Here's another example. We have a rotational slide and slump. This is again from my travels in Nicaragua going up the side of Concepcion, the active stratovolcano. You can see here as I look down the side of the mountain and we zoom in on it, you can see that these are breaking away, right? You have this little landmass that's rotationally breaking away from that landmass, which is breaking away. See another example here, right? This has some characteristics where you could either call it a translational slump because it sort of has this stepwise pattern, but it's also sort of has rotational characteristics too, in that obviously this is sort of a concave kind of separation of land. I know this is all just a little bit confusing in that distinction between translation and rotational. And I don't want you to be too concerned about the differences. As we go back here, I'll go back here and you can see sort of what the differences look like. Translation, again, it's going to be a little bit more of a straight line. Rotational is going to be, you're going to have a little bit more of a curved action, a curved indentation in the land. All right, so what causes mass wasting? Well, in the slow examples that we're taking a look at, that was caused mostly by either temperature or freeze-thaw action in combination with gravity. And frankly, gravity is sort of the key element that is shared amongst all mass wasting events. What about faster mass wasting events? Well, those can be caused by earthquakes, by volcano, by water management, excavation. It's actually quite common, especially in pit mines, open pit mines, to have occasional slides and slumps, as well as occasional flows too. We also see it with rainfall can, of course, create, for example, a mud flow, for example. And then some of my experience is that when I've been out in West Texas and hunting down near the Rio Grande, I have some, I remember when I was a young kid, I was traveling with some yahoos, for lack of better words, and they saw an opportunity to cause an event, a mass wasting event, by just firing guns at the side of a hill. So really it can occur via lots of different methods, but just be aware that mass wasting has a lot of triggers. All right, so assignment 3, I'm not sure if I'm going to be able to post it either today or I'm hoping to get it online and on Sakai by Thursday. Assignment 3 is going to allow you to investigate mass wasting in greater detail. I think it's a pretty cool topic, and I hope y'all do too, talking about like landslides and mud flows and avalanches. I think that's really neat. So assignment 3 is a combination Google Earth assignment and editorial, and it's going to be due right at the end of the semester on November 16th, which, believe it or not, is actually coming up really soon. I thoroughly, highly, very much, I mean, every sort of adjective you can think of in terms of encourage, I really encourage you to start early. This assignment is going to be a little bit more complicated than assignment 1 and assignment 2, mostly because you're going to be collecting data almost on your own in Google Earth. And it's going to be data in terms of like the slope of a landscape and trying to figure out what sort of mass wasting event occurred. On top of that, and for those of you who are unfamiliar with Google Earth, I especially encourage you to start early because this is going to be a new piece of software that you're going to have to deal with. On top of that, you're going to do create an editorial. And an editorial for, it's going to be a hypothetical editorial for a newspaper in Denver. And this is a really important technique that you need to learn as a scientist. As geographers, we are often called on for our expertise and to provide a little bit of knowledge for whatever research that we're doing. Unfortunately, some geographers have a hard time communicating with the general public, and I don't want you to have that problem. I want you to be able to communicate science to the public and make it important to the public. Right, I want them to be aware of the importance of your scientific research. And so what this is going to force you to do is just do a little bit of research as well as put together an editorial. And if you haven't made an editorial before or tried to put together an opinion piece, I include a lot of instructions to help you in that process. So again, please, please, please start early. Do not wait until November 14th, which I believe is actually a Saturday. You don't want to be doing this last minute. Start early, ask questions early, and both Kriti and I will help you through it. Okay, like I warned you at the beginning of today's class, it's time to do something completely different. But in some ways, I think it's a good bridge. So what we've been talking a lot about is weathering, right? And we've learned a lot about weathering in the way that gravity and temperature and precipitation all act on the landscape. But one of those things that your book really does a poor job explaining is just sort of like water in general. And perhaps that's more suited for a hydrology class. But I think y'all should be aware of some of the various characteristics of fresh water. And this will set us up nicely for when we begin to talk about fluvial geomorphology, or put in sort of layman's terms, we're going to be talking about how rivers change the landscape. And we're going to be starting in on that both next week as well as the week following, and sort of continuing with that same thing whenever we begin to talk about glacial geomorphology. And so I'm going to spend the rest of today's class as well as Friday's class talking about fresh water in anticipation of those geomorphology lectures. All right, it's been about 25, 30 minutes now. I'm going to take a quick break and grab some water. I encourage you to do the same.
All right, welcome back. So one of the key things that we need to recall back from the first part of the semester when we begin to talk about fresh water, and frankly when we begin to talk about the other sorts of geomorphologies later in this semester, is going to be talking about the hydrological cycle. Now, this all looks probably pretty familiar to you, and frankly, you may remember this from the first part of the semester, but it's just important to remember that water passes through lots of different stages, right? It can be evaporated out, goes up into the clouds, it condenses and then falls as precipitation down onto the Earth's surface, where it can then either fall or it can either flow through the rivers, or it can seep underground through infiltration and pass into either the water table or into an aquifer, which is more or less the same thing, or just sort of flow out into the ocean again. Like I say, today we're going to be focusing a little bit more on the subsurface kind of groundwater that's associated with the hydrological cycle. So what do we say when we think about groundwater? Well, we're really talking about aquifers, right? And this links pretty closely with the geologic focus that we've been having for the past several weeks, because you need both a certain sort of rock, as well as a certain sort of soil, as well as a certain sort of surface environment, precipitation environment to create an aquifer. And so an aquifer or groundwater is just water that is present beneath the earth in the soil pore spaces and in rock formations. Groundwater accounts for about 2% of all the water found on Earth. And in North Carolina, we actually see a fair amount of groundwater. An aquifer is just, like I said, underground layer of water-bearing permeable rock. And something to keep in mind is that often you see aquifers portrayed in figures as being an underground lake. Heck, even this figure up here from the USGS sort of gives the feeling that you're looking at an underground lake. It's not. It's not. Well, I say that. Vast majority of the time it is not. Often it's just water that happens to be found in the space between soil and sand and other sort of subsurface materials. Now, what does this look like in North Carolina? In the western part of the state, we have a lot of aquifers, but they're going to be a little bit more localized. They haven't been quite as named, and they can be a little bit discontinuous. So you may have an aquifer in the western part of a county that may not exist in the eastern part of the county, or maybe a separate aquifer, and that's partly due to the mountain location in which those aquifers are found. In the eastern part of the state, we see there is an extensive amount of aquifers, an extensive number of aquifers. So here we have this this particular figure from the USGS. And what this is looking at is the number of aquifers starting from here, basically, I don't know, maybe 50, 60 miles east of Chapel Hill, and going all the way out to the ocean, right into the bays. And so we can see here that there are a fair number of aquifers that exist just in this little cross section. As we travel further and further east, we can see that the aquifers become a little bit deeper and deeper. And what else do we notice about the aquifers? Well, we notice that there may be multiple aquifers in the same amount of land. So not too far from Chapel Hill, you're going to have the Surficial Aquifer, and then another one, the Black Creek Aquifer under that one, and then under that you're going to have the Lower Cape Fear Confining Unit. And each one of these has its own characteristics and its own sort of permeability, its own amount of like water content. And you can see that they're sort of broken apart by these pieces of base or of bedrock, right, that separate one aquifer from another. And we're going to talk about that a little bit more in just a second. So there are different types of aquifers and different sorts of ways to label aquifers. You can have a confined versus an unconfined aquifer. So a confined aquifer is an aquifer that is trapped underneath some bedrock, for example, while an unconfined aquifer is an aquifer that has direct access to the surface. And in fact, you may only have soil between the unconfined aquifer and the surface. And you can see in this particular example, which I think is a really cool example, right? You have a high hydraulic conductivity aquifer, which means that whenever it rains on the surface, the aquifer is going to be directly impacted. Whenever there's a drought on the surface, the aquifer is going to be directly impacted. Then you have this sort of geologic break, a layer of rocks or stones or bedrock, where it's very difficult for the water to pass between the unconfined aquifer and the confined aquifer. And then below you have the confined aquifer, which, just as the name implies, it means that it's trapped underneath a piece of bedrock and really is inaccessible. And then, of course, you have this sort of gray stuff around the outside. That's low hydraulic conductivity bedrock, which just means that there's not hardly any water that's going to be in this bedrock over here. So you have confined versus unconfined. You also have saturated versus unsaturated. And this is pretty straightforward. I mean, when an aquifer is completely saturated, that means it's completely filled with water. It can't accept any more water. And so that water either sits above the aquifer and makes the soil more damp, or it somehow is evacuated away from the aquifer. An unsaturated aquifer, on the other hand, means that there's still some amount of pore space. There's still some ability to stuff more water into the aquifer. And you can see an example here, right? We have the unconfined aquifer, which is probably fully saturated, and then you have what the figure authors have here as the unsaturated zone, an area where there's still the opportunity to have a little bit more water. All right, and then we have the third sort of main categorization associated with aquifers, porous aquifers versus karst aquifers. And so a porous aquifer is an aquifer that you're going to see probably most frequently. And a porous aquifer has a lot of soil, sand, and dirt. And what happens is that the water infiltrates down into that soil, sand, and dirt and sort of coexists with it, if you will. And so here where I live, just outside of Fort Worth, I live on what's called the Paluxy Aquifer. And what it is it's a porous aquifer. You drill a well down into the aquifer, and there's a lot of sand and dirt and soil. And whenever we suck up water, there's a series of filtration systems that are able to sort of capture as well as disassociate the water from the sand, soil, and dirt. A karst aquifer, on the other hand, occurs in karst landscapes, and we can see an example here. And it's in those limestone landscapes where, you know how I said earlier, it's not very often that you encounter sort of aquifers as an underground lake, but in these karst landscapes, sometimes you actually do see that, right? And it's whenever you have these giant caverns that are able to capture and hold lots and lots of water. We have an example of that here, as I'm going to show you probably on Friday, here in Central Texas, or down south of here in Central Texas, basically near San Antonio and Austin on the Edwards Aquifer. And in that aquifer, what you find is that it's easily recharged by precipitation, because you have all these disappearing streams that pass into sinkholes that go down and immediately recharge the aquifer. And in those situations, you're able to keep really close tabs on the status of the aquifer, its depth, its water quality, things of that nature. There's another sort of type of aquifer that I want you to be aware of, and that's going to be the fossil water or fossil aquifer. And so, whereas if you have an unconfined aquifer, it may take, a couple of days or weeks for the water to kind of sink through the soil and get into the aquifer. Whenever you're talking about a confined aquifer, that might take a couple of centuries, especially if it's the first confined aquifer underneath a layer of bedrock. What happens if you go even deeper? Well, sometimes if you go really deep, there's several layers of bedrock that separate the aquifer from the surface. And the water, whenever it infiltrates down into the soil, it may take centuries or even millennia to reach those kind of deeper aquifers. Fossil water is that same idea, except it's water that infiltrated into an aquifer millions of years ago, and it takes sometimes it may take thousands to tens of thousands, hundreds of thousands, or even a million years for that water to get from the surface all the way down into the aquifer. Sometimes though it may recharge relatively quickly. And we can see some example of this here, right? Let's take a quick look. This is northeastern Africa. We have Libya, Egypt, Sudan, and Chad. And in this particular region, there's the Nubian sandstone. And the Nubian sandstone is an aquifer, or at least sort of a water-bearing rock. But in some of that water that's in there is 4,000 to 20,000 years old. Now, if there was a lot of rain in this region, then that aquifer could probably be recharged relatively easily. But it exists in the Sahara Desert, and therefore it's really not very often that that aquifer has access to high levels of precipitation. And so what you find is that some of that fossil water, some of that water deep underground, may be upwards of 20,000 years old. Some of the water that you find, some of the groundwater that you find in Saudi Arabia, just to the east of here, some of that groundwater, aquifer water, may be hundreds of thousands of years old, or even a million or more years old. And so what are some of the social implications of pumping fossil water? Well, one of the biggest implications is the fact that you may only get to withdraw it once in the lifetime of hundreds, if not thousands, of generations. You may only have access to that water once, right? Once you use up that water, it's gone. It may take tens of thousands of years, or even a million years, to recharge that aquifer. So in these situations, you have to be especially careful with managing your water resources prudently. What about aquifers in the United States? Well, the USGS has put together a map that shows all the primary aquifers in the United States. And we can see that aquifers, stretch across the vast regions of the United States. And that even in locations where it's really arid, such as out in the western part of the country, you can still encounter aquifers. Now, this map is a little bit deceiving because it doesn't tell you anything about the quality of the aquifer, the amount of water in that aquifer, or even whether that aquifer has salt water or fresh water. And so, while this gives the perception that the United States is just chock full of groundwater, the reality is a little bit more complicated. And in fact, there are only a certain number of aquifers from which you can easily extract fresh water that can be used for daily uses. All right, let's go ahead and wrap things up there today. We'll continue with our discussion of aquifers on Friday, as well as begin to talk about surface freshwater. So what have we covered today? Today we took a look at mass wasting, taking a look at the three main types of mass wasting: falls, flows, and slides. We also talked a little bit about assignment 3, and again, it may not be posted on today, but I'll do my best to probably get it up there probably by Thursday. And then the second main topic that we talked a lot about today was groundwater. How to characterize groundwaters, whether they're porous groundwater, porous aquifers versus karst aquifers, or whether it's a saturated aquifer versus an unsaturated aquifer. We also took a look at fossil water and the importance of managing the resources associated with fossil water very prudently. All right, I think that wraps things up for today. I hope you have a great rest of your day, and I look forward to seeing y'all on Friday. I believe Friday is going to be a live lecture, so go ahead and if you have time, stop on by and stop into class, and we'll be chatting about water as well as water rights. All right, thank you.